Dear students, in the last video we have discussed about the importance of size and size distribution of the nanoparticles, and also we have discussed about the various parameters that indicate the size and size distribution of nanoparticles. Okay, diameter of the particles indicates their size, and polydispersity index of the particles or polydispersity index of the particles of a powder or a dispersion indicates their size distribution. And in the last class we have also discussed about the various formulation as well as process related factors affecting the size and size distribution of the nanoparticles in their dispersion. And today we'll discuss about the various methods used in the determination of size distribution, and the morphology of the nanoparticles. Okay, and among all the methods available, three methods are commonly used, okay, for determination of size distribution as well as morphology. They are photon correlation spectroscopy, atomic force microscopy, and electron microscopy. Okay, coming to photon correlation spectroscopy, it is an established technique based on dynamic laser light scattering due to Brownian motion of the nanoparticles in the dispersion. Okay, and this method is most suitable for measurement of particles whose size ranges in between 3 nanometers to 3 millimeters. And the device, okay, what we call it as photon correlation spectrometer consists of a laser source, a temperature controlled sample cell, and a photomultiplier for detection of light, scattered light. Okay. Using this method we will determine a diameter, and we will call it as photon correlation spectroscopic diameter. Simply we can call it as PCS diameter, and this diameter is based on the intensity of the lights scattering from the particles, okay, from a nanoparticular dispersion. Okay, nanoparticles are generally polydisperse in size. Okay, already we have discussed about polydispersity index. Okay, and for for part for a monodispersed powder or for a dispersion containing, okay, particles of all particles of same size, the polydispersity index is theoretically zero. But for practical purposes, uh, for practical purposes, uh, the polydispersity index for such powders and nanoparticular dispersions, okay, will be will can be allowed up to a value of 0.05. Nothing but polydispersity index value can be allowed up to 0.05. Okay, for for more for nanoparticular dispersions or powders containing very narrow size ranged nanoparticles. Very narrow size ranged nanoparticles. Okay, but when polydispersity index becomes greater than 0.5, it indicates a broad size distribution. Okay, so using this technique we will get the data of the diameters, that is nothing but data of the PCS diameter. Okay, and using this data we will calculate the mean PCS diameter. Okay, and this mean PCS diameter indicates the average diameter of the dispersion, nanoparticular dispersion being studied. Okay. Uh, the usage of the extent of usage of this method depends on its ease of operation and the speed with which one can obtain the data. Okay. Generally, samples that are to be prepared for this technique need need to be diluted in an appropriate solvent. Okay, which is usually a filtered water, which is usually a filtered water. So this is about photon correlation spectroscopy. And coming to atomic force microscopy, this is an advanced microscopic technique and is applied as a new tool to image the original unaltered shape and surface properties of the particles. In this technique, a small probe is brought into close proximity uh, to a surface of the object. Okay, and I'll say, okay, a probe is brought in close proximity to the surface of the object, whereupon the surface the nanoparticles are located. Nanoparticles are located, okay, or arranged. Okay, and this technique uses the force acting between the surface and the tip of the probe, resulting in a spatial resolution of up to 0.1 nanometer for imaging. Okay, and the main advantage of this technique is that simple sample preparation. Why? Because this technique will not require the use of any vacuum, and the sample need not to be electrically conductive in nature. Okay, so these are the main advantages of this technique. Okay, simple sample preparation and no need of electrically conductive sample. Hence, this technique allows the analysis of both hydrated as well as solvent containing samples. And finally, the speed at which this technique gives the images is fast enough to permit the observation of in situ processes occurring at the interface. Okay, and for the investigations using this technique, the particles are fixed on an appropriate smooth substrate surface to allow a clear-cut distinction between the particles and the surface. Okay, there are two types of imaging using this technique. First one is non-contact mode imaging, and the second one is contact mode imaging. For non-contact mode imaging, standard polished silicon water surface with a roughness below 1 nanometer can be used to place the nanoparticles. In case of contact mode operation, the tip touches the sample surface. The tip of the surface of the substrate touches the sample surface, nothing but surface of the nanoparticles, and may result in alterations of the sample surface, such as removal of the particles from the area under the investigation. And this can be avoided. This disadvantage or this problem can be avoided by fixing the nanoparticles on silicon water surface, which was roughened to the values of up to 10 nanometer by etching the wafers hydrofluoric acid and ammonium fluoride. and the measurements are usually performed under ambient air conditions, and monitoring the force acting between the tip, nothing but probe tip, and sample while the tip is approaching the sample surface can reveal the hardness of the sample. Okay, so these are the important details about atomic force microscopic technique for uh, for the determination of part, particle size and particles morphology, etc. And the third technique is electron microscopy. Okay, we have two types of electron microscopy microscopic technique. Two types of electron microscopy are commonly used in determination of size and morphology of nanoparticles. They are SEM and TEM. Okay, SEM. SEM stands for scanning electron microscopy, and TEM, okay, TEM stands for transmission electron microscopy. Okay, this both are electronic microscopic techniques. Is whatever may be the technique, SEM or TEM, they allow the determination of particle size and size distribution apart from the morphology of the particles. Okay, between these two techniques, SEM is most commonly used, most widely used. Okay, uh, because it is less expensive and easy to perform, and when compared to TEM. Okay, and SEM uses electrons transmitted from the specimen surface, while TEM uses electrons transmitted through the specimen. Okay, SEM has high resolution. Okay, nothing but SEM gives images of high resolution, and sample preparation is relatively easy in case of SEM. Okay, but the nanoparticles must be able to withstand a strong vacuum, and they have to be conductive in nature or electrically conductive in nature in order to be uh, used in SEM technique. This is a disadvantage. Why? Because for making the nanoparticles electrically conductive, will give a metallic coating onto their surface. Usually gold is used as a metal for give a coating onto the surface of the nanoparticles. This may often modify the original surface characteristics of the nanoparticles. Original surface characteristics of the nanoparticles. Okay, dear students, so this is I will end with this in this video. Okay, and I will continue the topic in the next video. Thank you.